I'm working in Clifford analysis, or hypercomplex analysis, function theory especially, and I wanted to present today some application of this theory for quasi-conformal mappings. But first of all, I wanted to remember Nore Arakelian, who passed away at the end of the last year. He was a great friend, older friend of mine, president of the Diploma Defense Commission. I remember very well, and he helped me to come back to Yerevan. It was a very good time. Last time I saw him 6 years ago when he was a celebration of 100 years of Jebashian, and he gave me as a present a bottle of wine, a rainy, and I will remember very well the time we spent together. And I mention here that he was in 70 already invited as speaker of the International Congress of Mathematicians at Nice, and this was the title. He succeeded at that time to prove or disprove conjecture of Van Lina, where he became famous at that time. So, but I will speak about this 3D quasi-conformal mapping with hypercomplex function. And in the beginning, I wanted to show you a building from Santander. You see, it's a sport palace, and I'm sure that you see some similarity. These are pictures produced as mappings with hypercomplex function, and by chance, we found this as the proof that there are buildings one could use this type of function, I think, for getting such constructions. In fact, when we started, we were contacted by engineers from Italy, but unfortunately, it was not possible to collaborate. Very interesting thing. The aim and scope is, as I told you, foremost to show which kind of monogenic function, of generalized holomorphic function, can be useful. It's not my aim to show you that the approximation with these functions are more accurate, but numerically very efficient. This is my aim, and so I will in the first part to show which type of function we are using. Then I give this example using a classical method of Kantorovich and Krylov in an old book of the 15th, where he showed very convincing a method which I will explain. And he has there in the books the example for mapping the square into the sphere, which is in the plane already a problem which leads to quasi-conformal mappings. As you know. So then, in the third part, I will show you that by introduction of some generalized appel polynomials, generalizing the power of complex variable z in a suitable way, very easy to count, can be also used. And in the last part, I will come to this picture you saw at the beginning, concrete approximations of spheres to not centered in the origin, of course, which give profiles similar to a 3D Joukowski transformation. That's behind. No? So, first of all, the algebraic background. We are using orthonormal basis. This is for functions in Rn plus 1. Of course, for 3D mappings, we use only paravector variable. This composition is called paravector. You have here the vector part and here the scalar part. Sometimes we are writing x. Still, this we can consider as reduced quaternions because by this rule, all the squares of such a generator is equal to -1. So it's a generalization also of, yeah, that's better. Thank you. I'm not so important. This is more important. Yes, and it's everything. And so the theory of monogenic or generalized holomorphic function is based on the idea that you have several imaginary units, n imaginary units, so that we have also the conjugated z, and then the matrix is here given by the product of z and the conjugated, and people are calling this also reduced quaternion. And for the function, we have the same form of a paravector. And the most important thing, which leads us to the analytic methods, is the introduction of an operator, linear operator, a generalized Cauchy-Riemann operator, in fact, which factorized together with this conjugated operator the Laplace, so that we have all the functions in the kernel of this operator also as harmonic functions. And then we have to take care that we are in a non-commutative algebra, so this operator can be applied from the left and from the right, and the function we are considering are in the kernel of this. And all this was possible after detecting 25 years ago, you see it here, with my German friend Klaus Göhlebeck, that we have also for this type, and this was not known before, some type of generalized hypercomplex derivative. And we started also with our students. Paulus Dergeras was mine, Uwe Kehler, the student of Göhlebeck. We started very early, 2001, also the consideration of all what concerns homomorphic solutions of a generalized Beltrami equation. We will listen about Beltrami equation later. So, but this was the beginning, and then we have to look to understand what happens to the corresponding system, real system, and this is called the Ries system. It's the easiest. One can consider much more complicated if one is looking for mappings in the algebra, in the whole algebra, Clifford algebra. But of course, for the real world problems, this is almost enough. And the most important condition which comes out here is this compatibility condition of the components of f1 and f2 of the function. You see, in fact, we have inside, if one function is 0, we have 3 times Cauchy-Riemann equations here. That's the secret of this. But what is peculiarity is that the ordinary powers of the paravector variable are not monogenic. They are not in the class, even z by itself is not monogenic, it's not holomorphic. So you have, if you're working with this variable, you have a variable which does not belong to the class of functions. And this is not comfortable. But if one uses a symmetric product defined over all permutation, there was a lot, 20, 30 years, the Belgian colleagues used only this presentation with different permutation. And this was the reason that they could not use in a very obvious way generalization of the binomial theorem and everything. Then the secret is here that you are using in this product all permutations. And then you can even notice that the symmetric product of the variable, of this hypercomplex non-monogenic variables with the generators leads to monogenic variables. So you are skipping from the consideration of a function of one hypercomplex variable to the consideration of a function of several hypercomplex variables. This is a very big advantage, and you see that we have even a very suggestive dual presentation. If you have several complex variables, you are in Cn, then you join 2 vectors of real variables by the imaginary unit. But here you join for the hypercomplex variables, they are not called Fourier variables. He started in the 30s in the quaternion sense, working with this, but not naming, not using as variables. They appear in the representation of the function, but he was not aware that they can play a starting point of all the theory, you know. But here you see you have a real vector and then the vector of the generators and one, the n plus 1 real variable. So the parallelity, the duality is here obvious. And maybe I skipped, no. Then it's important that if you use these variables to consider a polynomial, a homogeneous, to get an idea about the structure of the functions, you see that because of the compatibility condition, we have the coincidence of coefficients of some A2 part and some A1 part of this coefficients, which you can use for such a function. And it's very clear, because you want to have similarity with a several complex variable case, you have to combine a convention with a multi-index. You consider this product in the same form, and you get here the vector of this an in the algebra written in such a form, so that also the form of the Taylor series and other things are almost the same as in the several complex variables case. And here we see the Taylor series of such a function written with these variables. And because you have that these variables are connected through the symmetric product with the paravector variable, you can this also write in terms of the paravector variable. But now it's almost clear that the defining structure comes from these variables. And then we can prove that these coefficients have to have equal parts in the E2 part and in the E1 part, because if you are differentiating this compatibility condition, now written with U2 and U1 instead of F1 and F2, that exactly this condition comes out, and then you see how it works. This is a sufficient condition, of course, but it can also, a necessary condition, but it can show that this also is sufficient condition by induction over K. So then you know very well how a function, which you would use for such mappings, and you know in function theory, you know the class of schlicht functions. No? We come here, in fact, to the generalization of schlicht functions, that this is coming from the condition, from the compatibility condition, the coincidence of this part. And then if you look to the theory of schlicht function, then you have that in the point 0, f should be equal to 0. The derivative, here is the derivative behind this conjugate d operator, should be 1. This means new restrictions on the real parts of the coefficients. And then you need a third condition, is another differential operator, in fact, because you are in higher dimension. Here only the minus sign appears and not the both, and you see that's a variation. And then you see that the first coefficient for the linear part should be 1/2, and you get the class of schlicht function in this sense. You have here, instead of z, which appears in the schlicht function theory, you have this. We determine the coefficients. And then you should take care that you have the coincidence in the real components of the hypercomplex coefficients. And as I told you, we looked to an old paper of a book, in fact, Kantorovich and Krylov, Approximate Methods of High Analysis. There you can find a big amount of methods, for example, for this practical things like conformal mappings. And we have chosen only by seeing how it works, and maybe it leads us to some restriction by some reason. And really, the complex case is this: you are considering the boundary of this domain you want to map, embedded with a small real parameter in a family of curves, parameterized, and then, in fact, to get the mapping, you have to determine by algebraic equations, and of course, with all the possibility of computers, you can do it very well, the value of this lambda. And so you can approximate in a well set. You see, this has to mean this method leads to the resolution of nonlinear algebraic systems. And you will see it in the 3D case, what this means. We did the same. And now we need two real parameters, not only lambda, also t. And then the coefficients of the function depends from what means in the complex case lambda has to be now twice. Then we can also the numerical costs essentially reduce if you have still in the As in the square case, for example, there's also an essential reduction of numerical costs when you look to the book. And also in our case, we have additional symmetry condition still, and so hyperplanes, and in the hyperplane we have symmetry, suppose. It's, as I told you, it's not for showing here the most general things for doing quasi-conformal matching, but as an example, because this will lead us to a set of functions which are relevant in this case. You see, and here we have axially symmetric, so the method works very well for axially symmetric domains, and here you see the coefficients come in, but they have to coincide in some components, and then here is the realization of this approximation. You see lambda appears as a parameter and also t as a second parameter for mapping an oblate ellipsoid, the inner, to a sphere. This is here as an example. And then, of course, that the mapping should lead to a sphere means that this module should be constant, and then it comes out. It looks a little bit strange. Nevertheless, with a computer, you do it very well and rapidly. You get here the values of these coefficients very easily. And of course, the number of the Pascal triangle appear here also. They have special rule. This is for approximation by a cubic part. And then this was, as I told you, very early. It was around, we did it with a student, 2007, 2008. We used Maple, and the other picture you saw was done by Mathematica, so that's much more. And my colleague, Yerevan, I mentioned in the beginning, she is a specialist in numerical conformal approximation. She was a student of Papa Michael, maybe you know from Cyprus, from Greece, yeah. And so it comes very well together. And these are, with other values of lambda, the images. But as I told you, when we saw this, that it works rather well, and the structure of the mapping function seems rather clear, it came to our mind that we could, instead of the complex power of Z, we could also look to polynomials as the adequate, the suitable generalization of this. But these polynomials are defined by these variables, Z1 and Z2. And yes, sometimes, and not to forget that you could have this also for the dimension n+1. We write also n, but here in this case we have only n equal to 2 written, and formally you see. And the additional condition we need for defining these polynomials is that you have an initial value, and then we were even not, let's say, not obliged to start with a definition of these polynomials by their monogenicity. But we could also, because I showed you how the coefficients are working together, we could also detect immediately by this initial value and the canonical expression of a monogenic polynomial, as I showed you in the beginning, we came to this form of these polynomials. And what happens, and this was after this a long time of work we are doing, that these coefficients which appear in the construction of such a polynomial, these are generalized Vietoris numbers. This comes from positivity. Yesterday, this word positivity was mentioned. And this was also a forgotten paper of Vietoris, a famous Austrian mathematician in topology and all the stuff, you know him. He wrote a small, some pages for the Austrian Academy, and where these numbers appeared, but only for the plane case. We had here now the generalized Vietoris numbers. And it's a nice sequence of numbers for the coefficients you find here, but there's one coefficient in all powers, you see, it's also important. But they are repeating. So there's a sequence of repeating numbers, and following a very strong rule, they are connected to the central binomial coefficients. We did also a lot of combinatoric research about this. We found the generating hypergeometric function, all this stuff, very exciting, and some connection with Sturm-Liouville problems are behind, even so that, but this is another history. Maybe next year, if I come back, I will speak about this combinatorical stuff. It's not so close to our subject, but it's really an exciting field. So, and if we are doing, then we have, for the example of a cubic approximation, we have, you see, this is already with the Vier-Torres numbers. The first is 1/2, then you have also in the square, you have 1/2 as Vier-Torres, but the monogenicity implied that it does not appear. And so we have for the cubic part this coefficient, and the rest comes here as should be. And this is a picture when you are doing this mapping with the method of Kantorowicz-Krylov, you see. So it becomes better and better if lambda is smaller, of course, it should be, and the error is already very, very small. And for 5th degree, we have here the ellipsoid, and then this ellipsoid is transformed more and more to the sphere, as it should be. And my colleague Klaus Gürleberg, later with a student from Portugal, I sent him to Germany. He continued a lot of consideration of mapping properties of monogenic functions in a very classical and non-classical way. This led him to Zernike polynomials in optical theories. So it is exciting. But he left and he is now working in Mexico City. And what was in the fourth part of my talk, yeah, I have time, I guess, was the idea now, 7 minutes, yeah, to generalize the Joukowsky transformation, because this is very interesting. You know, airfoils are molarized by this. And what happens here that for the 1 by z in the classical Joukowsky transformation, we needed to rely on the fundamental equation or fundamental solution of the generalized Cauchy-Riemann equation. And this is, of course, the definition of fundamental solution. And this function is that function which appears here for the negative power part, in fact. And you get it by differentiating the fundamental solution. This is the form of the general solution. Yesterday also it appears in one talk, but from the real point of view. And then what is interesting that this fundamental solution, the Cauchy kernel, in fact, generalized, is connected, is the basis for getting the Kelvin transformation. The Kelvin transformation gives you transformation from outside to inside of the circle and vice versa. And then it's possible to understand that this generalized Joukowsky transformation can be expressed poorly by these Appel polynomials. Here you have the positive power part, and here the negative through the Kelvin transformation. And you can see the general writing is here. And also what I would like to mention, we did this also not only for the case k equal to 1, but also for this generalized Joukowsky transformation of order k. It's not so well known, but there were papers in the 90s about functional equations. There Chebyshev comes in, Joukowsky implies relationship to Chebyshev's functions. And so a lot of analysis is behind. And that's very exciting that the non-commutative structure of the algebra can combine this in a very interesting way. Bessel functions, somebody spoke also about Bessel yesterday. So all comes here from the hypergeometric part into consideration. And here we have the expression of this generalized Joukowsky transformation only by this Appel polynomials. This is also very important, and a lot of people are now working in hypercomplex analysis. For example, Alpay and the group in California, they wrote 4 years ago a paper about these variables, and 2 chapters of them were my results from the 90s. They developed it more, and Yeah, but we have also done things about generalized polynomials, the Laguerre polynomials we generalize, and so very, very nice analysis comes in. And this is what I learned here, that mathematics, if it's possible, could also be an aesthetically very demanding, or it's a nice thing. No? And this, what I want to show you now for the, you see in 2008, the first publication, for the case k to 1, of course, this coefficient which appears here in the general form, alpha k, is differently from every k, it depends from k. Here's 2/3 comes in, and then you have the explicit form. And then it was also necessary to get a nicer presentation, to change the real axis with the imaginary axis. So this is very well justified. So to work not with the polar or spherical coordinates, but with the how it's called, geological version. No? You have this way, and then of course you have double coverings, and the pictures are now interesting because you have here such a type of ellipsoid. Then you have the case for a special value of rho, but still with the mapping of the domain in the 0 point in the center. So then you have this picture, but if you, and now comes the nice picture, if you change the center of the starting domain, then you get such nice pictures. And you see these are cutting, you see here the airfoil is coming, but in now together in for R3. And if you are doing this for k equal to 2, here is description of this different type of spheres. Here we have also some special values. It's like if you in Joukowsky are considering the outside or the inner part of the unit ball or unit disk, that you have different behavior, and here the numbers are well determined. We have all the estimation which you need for quasi-conformal mappings, and then we have fourfold mappings in this case, and then we have the other picture, the second picture I showed you, as a result of this application. This is all. Thank you very much for your attention.